I'll update the point as follows: is equal to xt minus eta times the gradient of the function at xt. That's all. At written. If you do it t times, written xt plus 1. Okay. Or I think let me x0 is fine. I think x0 is fine. Okay. Fine. Now, geometrically, what is it that we are doing? Is this clear from the diagram? So this is what you are doing, right? You take some point x naught in the domain. You are going to find the gradient of that at that point. So this will be the gradient, right? Now I'm going to move an eta distance in the direction of the gradient. So if I take the gradient, what will you get? You either get positive or negative, right? Here, what is the gradient? Huh? Positive or negative? It's negative. So if I just add the gradient, I will move in this direction. Do I want that? No, right? I want to subtract. So that's why you have minus here. Minus eta times gradient. So I'll move in this direction. So I'll take what is this point, right? So this is x1. Again, find the gradient, right? It's negative. Negative of negative is positive. You move some distance here and keep on moving. After t times, you stop, right? This is the algorithm. But now, what are the questions? Suppose you came up with this algorithm several hundred years ago. What is the first question that you will ask? Huh? Of course, now you just program and see if it works. If it works, you'll say, I don't care, right? That's how, I mean, that's how we approach the problem nowadays. But what are the other interesting questions you can ask? Huh? Okay, so when and where to stop, that means how do you choose T, capital T, right? Okay, that's one question. So when do you stop, or what should be T? And then, huh? Sorry? Beyond? No, you should be louder, man. You have the mask and. So what you are saying is, well, instead of stopping here, you go here, right? Well, that can happen, right? So you go here, then it's negative, then you go here, then it's positive, you go keep on oscillating, right? Well, when will this happen? Oscillation? When eta is fixed, right? It will keep oscillating. If t is infinity, capital T is infinity, it will keep oscillating. So how do you avoid oscillation? You decrease eta with time, right? With the iteration also. So it will take smaller and smaller step. It doesn't oscillate like this. It oscillates like this, slower and slower and slower, right? That's how it happens. Anyway, that is one thing. How do you choose eta? What else? First of all, whether it can stop. I mean, eventually it will go to the minima, right? That is another question. If so, how fast? Right? If you want to be epsilon close to the minima, how many steps should I take? So these are many questions that you can ask, right? So let's try to answer some of them, and in doing so, we will look at some of the very, very interesting. We'll make some interesting observations, and we will see some interesting mathematical quantities, which will be very, very useful, even if you look at deep neural networks and ask why deep neural network works, right? Do you know why it works, by the way? For those who have taken PRML, do you know why it works? It works, probably would have run it on many data points, and it works many a times. It works really well if you have deep neural network, but it's not very well understood. People have understood a little bit now. I mean, they have some understanding, but back then, it was not very well understood, right? So some of these inequalities are very, very so useful that it will actually explain why it works. Okay, let's look at the analysis, right? So let's probably start the analysis and maybe continue in the next class. So what is it that I have to prove? I have to prove that if I do gradient descent, right, I will eventually converge. That's the point, right? So let's see proof of convergence. So I'll write this as a heading, and then in the next class maybe we will write the statement of the theorem, right? Convergence. of gradient descent.